Hello everyone, how are you guys? Yeah, so today we will have like four questions which will be dealing with mechanical metallurgy as well as processing of like how welding is taking place and what are the different types of processes like fusion welding, which is the solid state welding. That type of questions we will take today. So I guess you both are joined for the first time, like Subramaniam and Shruti. So what I will do is basically I will project one question on the screen. I will give you 2 minutes to answer. You can either enter it on chat box or just convey by unmuting yourself. So I will give you 2-3 minutes to solve that question. Then we will go through the exact solution of that question. So last time I took two questions, but as very less students were present last time, I will repeat those two questions and then we will move on to the fresh questions. So let me project my screen. I hope you can see my screen now. So I will project first question, and you have like almost 2-3 minutes to solve that question. Then we will go through next question. So these are the questions of GATE 2012 question paper, metallurgical engineering. So first try to solve question number 14. I will give you 2-3 minutes to solve this question. You can enter the answer in the chat box. Here the strain hardening behavior function is given of a cold rolling annealed rod, and you need to know that you need to find out the flow stress after 50% reduction in area. So I will give you one hint that you need to find out first the true strain in the material when it is reduced to 50% of area. If you find that, you just need to put that in the equation and you will get the answer. Just try to attempt this. After that we will go through complete solution. One more minute to solve it. First only solve question number 54. Then I will give you another 2 minutes to solve 55. Option B. Okay. I will give you like 30 seconds more. Just check whether you will get that thing. Okay, let's solve this question. This is question number 54, GATE Metallurgical Engineering 2012 question paper. The strain hardening behavior of an annealed rod during cold rolling is given by sigma equal to 700 into epsilon raised to power 0.2 MPa, where sigma denotes the flow stress at strain epsilon. So we have to find out that the flow stress after 50% reduction in area of a annealed rod on cold rolling is approximately option A is 750 MPa, option B is 650 MPa, option C is 609 MPa, and option D is 559 MPa. So let's start with the solution. Given is, we should write first the equation of flow stress. Sigma is denoted by 700 into epsilon raised to power 0.2 in MPa. Okay, so this is the equation given, and what asked is like 50% reduction in area. So we know that AF is 0.5 of A initial. Now what is the equation of true strain, which is given by epsilon, which is ln of A0 by AF. Okay, so which is equal to, we will keep A0 as constant, so it will be ln of A0. AF is basically 0.5 of A0. We will write it as A0 by 2, which is equal to ln of 2, which is equal to 0.693, which is, this is true strain when the material is deformed till 50% reduction of area has occurred in the material. Now we can substitute this value in this flow stress equation, which is given by sigma equal to 700 into 0.693, which is the true strain, raised to power of 0.2, which comes out to be 700 into 0.93, 93, which is equal to 650 MPa. So the correct answer for question number 54 is option B. If you have any doubt, you can ask me now of question number 54, then we will solve question number 55. Is it clear, this question? Basically you just need to like evaluate the true strain at like what is given, like 50% reduction in area. It can be anything like 25%. Depending on that, you need to evaluate the true strain and just put it into the equation. That's all you have to do. Is this fine? Shall we move on to next question, or you have any doubt in this question? Okay, so let's move on to question number 55. I will give you like 2 minutes again to answer that question. This question is bit like tricky because the final answer is not given in the option correctly. So you will have to see. I will again showcase you the question, which is 55, and answer of this question is not in the above option. So this was like all marks were given to all of the students because the correct answer was not present in either of these four options. So I will give you 2 minutes to solve question number 55. Here the same thing is there, just we have to find out the drawing stress here. If you know the equation of drawing stress, like how you evaluate that, you will be able to tell the answer. You have to follow the similar procedure. First find out the true strain, then after you find out the true strain, you need to find out the true stress, and from both this true stress and true strain, you need to evaluate the drawing stress. And you have to here neglect the effect of friction and redundant work, which is there in the deformation process. I will give you 2 minutes. You just try to solve this question. Please follow the same steps which I did for question number 54. Here the wire of 5 mm diameter is drawn from 10 mm diameter wire or rod. So again one hint, you need to calculate the area initial, area final. If you know both these things, you will calculate true strain of the material. If you know the true strain, you know the flow stress of the material, and if you know the formula of drawing stress, you can evaluate the you can easily calculate drawing stress if you know the formula. One more minute to solve. As these answers are not correct, A, B, C, D, so you write the value of the drawing stress in comment box. I find no answer here. Shall I start with the solution or you require more time? I will give you like 30 seconds more. You just try it once. If not, we will proceed with the answer. Okay, then let's proceed with the answer. I will delete this. This is question number 55, GATE Metallurgical Engineering 2012 question paper. If a wire of 5 mm diameter is drawn from the above cold rolled rod of 10 mm diameter, the drawing stress, neglecting the effect of friction and redundant work, is approximately. Options are A 650 MPa, option B is 550 MPa, option C is 450 MPa, and option D is 400 MPa. So first, what is given we will write. Given is D initial. D initial we know is as 10 mm. So from that we will calculate A0. A0 is pi d square by 4, where D is 10 mm. Okay, so this is 1. Now we know the final thing, which is DF. DF is basically 5 mm, which is, then again we will calculate AF on the basis of that, pi 5 square by 4. This becomes equation number 2. Now we have to calculate true stress on the basis, true strain on the basis of D0 and DF. So epsilon is equal to ln of, again, A0 by AF. This is the standard formula of true strain. Again we will put the same values, as 4 and 4 will be cancelled. This will be basically ln of pi 10 square by pi 5 square. So pi gets cancelled. 100 square is 10 square is 100. So this becomes 100 by 25, which is basically ln 4, and ln 4 is 1.386. So when the wire is deformed from 10 mm dia to 5 mm dia, 1.386 is the true strain in the material. So from this we can calculate the true stress. True stress is basically the flow stress. For that we have the equation raised to 0.2. So 700 into 1.386 raised to power 0.2, which comes out to be 700 into 1.067, which is equal to 747 MPa. So we know true strain, which I will give as number 3. We know true stress, which I will give as number 4. Now drawing stress is given by sigma d, which is equal to flow stress into the true strain of the material for this flow stress. So the correct answer is 747 into 1.386, which comes out to be 1035 MPa. So the correct answer for question number 55 is basically 1035 MPa, which is not available in all the 4 options. That's why marks were given to all the students that time. So if you know these equations, basically this both the questions were dependent on this fundamental formula which they had given. This is basically the equation of plasticity, where sigma is given by this equation. flow stress is given by this equation, and in both the cases you needed to find out the true strain of the material. If you know the true strain of the material, then you will be able to find the flow stress of the material. And in question number 55, one additional step was there. Flow stress is not equivalent to the drawing stress. So drawing stress is given by this formula, if you know. So you have to find out drawing stress, which will be given by flow stress into the true strain of that material for that particular flow stress. So the correct answer is 1035 MPa for question number 55. If you have any doubt, just ask me. Then we will move on to the next question. If this thing is fine, then we will move on to the next question. In next question, then I will talk about like few mechanisms and few strengthening things. So basically it will be again a mixture of strengthening mechanisms as well as mechanical metallurgy. So I took this question last time, but many of you were not present. So let me go to that question. Yeah, so we have to in this question it is stated that group 1 is basically the different phenomena in mechanical behavior. Group 2 is the mechanism which is governing that phenomena. So you have to like match the following from group 1 to group 2. So group 1 consists of fatigue, creep, strain hardening and yield point phenomena, and group 2 consists of grain boundary sliding, slip band, extrusion and intrusion, quartet atmosphere and dislocation interaction. Now you just have to tell, you have to match the correct phenomena with the underlying mechanism. So I will give you 2 minutes, you just try to answer it. I have shown you here few schematics. From that I will like tell you how the things are in all the four phenomena. Firstly you try to solve it, otherwise I will proceed with the solution in 2 minutes. One more minute and then we will go through the solution. Has anyone answered? Option C, Subramanya. Okay, we will see. I have given you enough time. Now we will proceed with the solution. Okay, so this is question number 43, GATE Metallurgical Engineering 2012 question paper. Match the phenomena listed in group 1 with the possible mechanisms in group 2. So group 1 consists of 4 different phenomena which are fatigue, creep, strain hardening, yield point phenomena. And group 2 are the mechanisms which include grain boundary sliding, slip bands, extrusion and intrusion. Third is quadral atmosphere, and fourth is dislocation interaction. So group 1 should be paired with group 2. Firstly, coming to fatigue. In fatigue, what happens is, like as you can see in this schematic, so a slip starts in a particular grain which is oriented in a preferential manner with the loading axis. So let's say when from this is the basic cycle of fatigue. So there is some sigma max and there is some sigma mean. So this is sigma max and this is sigma mean. So what happens in fatigue is, like when this cycle is going towards sigma max, the dislocations moving on this plane are pushed forward, or they are moving in a particular direction. Till this point, like till sigma max, this will move in a particular direction. Now when the cycle is reversing and going towards sigma mean, what will happen is, like this dislocation will try to move in opposite direction. So what happens is, like for till when the sigma max is getting reached, they are moving in this direction, and when sigma mean is there, they are moving in opposite direction. And what happens is, like till sigma minimum is reached, this dislocation which was moving in a particular direction, now when it is moving in opposite direction, it cannot come back to same position, which we often term it as slip irreversibility. So basically the dislocations which were moving in a particular direction again cannot come back when sigma mean is achieved to a same position. This what it makes is, like this makes extrusion and intrusion. So basically this is basic roughness of the surface. This creates additional roughness on the surface. Now you can see this part of the material is plastically deformed out of this original surface, and whereas some parts are there which are like inside the surface. This creates the roughness, and these intrusions which are formed here act as a notch for crack propagation. Hence fatigue crack always initiates on the surface or subsurface because of this thing. So it creates additional notch. If additional notches are created on the surface, it acts as a stress concentration near this notch, and the fatigue crack will initiate after that. So the slip band extrusion and intrusion is related with fatigue. So P is connected to 2. Now coming to creep. What creep is? Creep is a phenomena where you have a material, you have applied a constant load to that material, let's say compression or tension, and you kept it at a temperature above 0.5 of melting. So the T here is 0.5 greater than 0.5 of melting. So this is the condition of creep basically. So what happens is, like if you can see what is grain boundary sliding. Grain boundary sliding is a material deformation mechanisms where grains slide against each other. So if you see this schematic, this is the polycrystalline material where the grains are arranged in a particular manner. So when you apply tensile load to that, so these grains will get elongated from here, and because of Poissonian contraction, this will become like this shape, because from here it will be compression because of Poissonian contraction. So this is tensile, this is compression. Now what happens is, like here lot of vacancies are created. because lot of vacancies are created because of this phenomena, what happens, this becomes an unstable structure. If the temperature is there required for diffusion, what will happen is like this boundary which is on the left hand side of this gap will try to move towards the right boundary, which you can see here. So if temperature is there required for diffusion of or migration of this boundary, then what will happen? This structure will be created. So this is basically the grain boundary sliding, because these gaps are highly unstable because of lot of vacancy accumulation. But the temperature is high enough such that the grains can easily slide on the top of, here you can see the grain can easily slide on the top of each other because the temperature is there for diffusion. Hence this grain will come close to this and join like this. So basic phenomena of creep is basically the grain boundary sliding. So for Q the correct answer is 1. Now coming to the strain hardening. So what is basically strain hardening is, if you have a tensile curve sigma epsilon, so first is the elastic deformation, then comes the plastic deformation. So what happens is like, so for every increment in strain you have increment in stress. So let's say these two mechanisms. So for every increment in strain you have increment in stress. So this is basically known as strain hardening. As you are straining the material, the stress required to strain that material up to a particular point is basically the strain hardening. So what happens is like, as soon as plasticity is there, like starts after the yield point of the material, the dislocation starts to move. Basically the moment of dislocation is plasticity. So when dislocation starts to move, they interact with each other. Interaction of dislocations. So let's say this dislocation interacts and it forms jogs. And as you know, jogs are a structure of two dislocations where they are pinned to each other. So if they are pinned, let's say I have a jog here, and so this is a pin dislocation and one dislocation is moving towards this dislocation. So what will happen is like, this dislocation will cause hindrance for this dislocation movement. Hence we will require additional stress for this dislocation to surpass this dislocation. Hence this, for every strain we will require additional stress. This is basically strain hardening. So N here. So what happens is like, this N is strain hardening exponent. So the value of N, the higher the value of N, more is the strain hardening is in the material. Hence all this strain hardening is because of the interaction of dislocations. Even here you can add interaction of dislocation to precipitates or dispersoids, precipitates or dispersoids, because these precipitates and dispersoids also cause hindrance in the path of dislocations if the microstructure contains these two things. Hence even more strain hardening can be achieved. So basically for this question, strain hardening is because of dislocation interaction. Now coming to the fourth thing, which is basically the yield point phenomena. As you may have known that in mild steel what happens is like, we get a certain type of stress strain curve. So it is basically like this, then like this, then again it starts to increase. So what usually the stress strain curve of all the materials is like this, but in mild steel we get this as some abnormality in the stress strain curve. So what this abnormality is basically because of the solute atoms and dislocations interact with each other. As you know that in mild steel there is very less carbon and nitrogen atoms. So basically what these carbon and nitrogen atoms do is segregate near this dislocation. So now this dislocation is pinned by carbon and nitrogen atoms. So we will require additional stress for making this dislocation free from carbon and nitrogen atmosphere. Hence, this causes this increase in stress which is greater than usual. So this is first yield point, or usually called as upper yield point, which is the stress required for this dislocation to be deepened from this atmosphere. Now, as soon as this stress is reached this point, the dislocation is free to move and it is not pinned by carbon and nitrogen atmosphere. Hence, the stress is dropped again here. So this is called as lower yield point. So this is the lower yield point. Still there will be some serrations here because the carbon and nitrogen are not completely detached from this dislocation. Hence it will move like this, and at this point these dislocations which are moving are like completely away from this atmosphere, which is carbon nitrogen atmosphere. Now normal strain hardening will begin, which will be governed by N, strain hardening exponent. So the overall atmosphere which is created by these solute atoms, which provide hindrance to the dislocation movement, is known as Cottrell atmosphere. And this atmosphere leads to this abnormality in behavior which is known as yield point phenomena. So S3. So the correct answer is P2 Q1 R4 S3. P2 Q1 R4 S3. So the correct option is option C. I hope this is clear. You can ask me any question if you have any doubt. Any doubt is there regarding this question? Okay, no doubt. Anyone else? Now these two questions I had taken earlier, so I will, like, on YouTube I will post this online lectures. You can go through that. I have taken these two problems again because these are important and keeps on repeating, like same questions keeps on repeating again and again. That's why I took it today also. Now I will go to basic two questions which are knowledge based questions. You will try to answer that and then we will close today's session. So I will project those two questions. I will do it one by one. So this is a knowledge based question. If you know, you can answer this question. I will give you like 1 minute time to answer it. Tungsten filament, which is basically used in electric bulb. You need to know what is the manufacturing process of that tungsten filament. Okay, try to answer this question. I will give you 1 more minute. Tungsten filament, how it is manufactured. Just comment in chat box which you feel that is the correct answer.
पहली बार ऐसे बोलते मस्त फुग्गा हुआ था।
Devendra, your mic is on. Please mute yourself. Okay, I will go through the answer, like how it is manufactured. This is question number 23, GATE Metallurgical Engineering 2012 question paper. Tungsten filament used in electric bulb is processed by option A is extrusion, option B is wire drawing, option C is casting, and option D is powder metallurgy. So the melting point of tungsten, first we have to know like what are the like melting point of tungsten is. So for tungsten the melting point is around 3400 degrees Celsius, and this tungsten filament gets heated up to 2000 degrees Celsius for its function in electric bulb. Okay, so we cannot melt tungsten up to 3400 degrees Celsius. Hence, casting is not a correct option, because in casting what happens is like you take the material to the melting temperature, completely melt that material and then cast it. So option C is not a correct option. So what happens is like the trend is basically tungsten is manufactured by powder metallurgy. So small powder of tungsten which will have a certain particle size is basically sintered. So first thing is, let's say these are the particles of tungsten, and now these are compressed so such that there are no gaps between these powders, and finally at higher temperature they are sintered so that you have a complete tungsten filament. However, this complete tungsten filament is very brittle, because tungsten has a property, it is very brittle. So what usually is done is like tungsten is like mixed with some amalgam and it is extruded. Some extrusion process they follow, so that it is not a pure tungsten, it is basically tungsten plus some amalgam, and this thing is completely extruded. So for this question the correct answer is basically powder metallurgy as well as extrusion. So these two are the correct answer for this question. That's why in 2012 all the like complete marks were given for this question, as it had extrusion as well as powder metallurgy. So firstly what happens is like it is a complete green body is prepared of tungsten, then it is sintered, which is basically the process of powder metallurgy. Now this tungsten is very brittle for its application, then it is mixed with certain amalgam and it is excluded out of that, which increases its ductility, and we can use it for tungsten filament in an electric bulb. So the correct options are option A and option D. As both the options are correct, all the marks were given to all the students. So this is fine, how the tungsten filament is prepared. So you should know powder metallurgy as well as extrusion. Both the processes are used in certain manner. Firstly, powder metallurgy, then its extrusion. Is it clear? Then I will move to the last question for today's lecture. So this is the last question. I will give you 1 minute time to answer this. These are four different metal joining processes and you need to answer which of the following is not a fusion welding process. First you need to understand what is the fusion welding process. One more minute, you just try to answer. Option D. Okay. What about others? Others are not responding. Try to answer. You can like go through this reading material also. I have given you the link of that. It will be available on nptel.ac.in where all these videos are there. So you go through these videos if you don't know the concept. Okay, so we will go through the solution of this. So this is question number 22, GATE Metallurgical Engineering 2012 question paper. Which of the following is not a fusion welding process? Option A is arc welding, option B is gas welding, option C is resistance welding, and option D is friction stir welding. So firstly, what is fusion welding? Fusion welding is a process where the temperature which is there in the process is greater than the melting point of the material. So basically what we are doing here is like the electrode is melting and it is getting bonded with each other. Let's say we have a two different workpiece and we need to bond this. So what happens is like we have an electrode and arc is created here. So and we put this electrode and move it throughout the length of this workpiece. So what happens is like lot of melting takes place and bond gets there. So this is basically a fusion welding process. So out of these options we need to find where the workpiece is not melted. So in arc welding basically this is the thing where the arc is created between between the electrode as well as the workpiece. Similarly, in gas welding also same thing occurs where we use gas to melt the workpiece. And for C, resistance welding, we use electric current. So basically, let's say we have two sheets here on top of each other. This is the first sheet and on the top of that another sheet is there. Okay, now we need to bond these two sheets. So what is there, like this is electrode 1 and on bottom there will be electrode 2. So what happens in resistance welding is like we pass large amount of current here through this. So this is the first electrode, let's say a positive electrode, and this is basically ground. So what happens here is like the current passes through this first sheet and it passes to the second sheet and then it goes to the ground. So what happens, this interface has lot of resistance, hence because the interface has lot of resistance, joule heating takes place. Joule heating is basically I square R T, where I is the amount of current which we are passing through the electrodes, R is the resistance of material, basically the resistance of interface which needs to be bonded, and T is the time for which we are passing the current. So what happens here is like as the interface is as having higher resistance, the heat generated near the interface is so high that it can locally melt the interface. So when you are locally melting the interface, it is getting bonded, and we, with the help of this two electrode also, we are pressurizing these two sheets. So this compressive stress is also acting on both the sheets, as well as local temperature near these two sheets is also higher. So here melting takes place near the interface and you get a weld here. So this is also known as spot welding. So in third option also, in resistance welding also, local melting occurs near the interface and it gets bonded. Now coming to the fourth thing, which is a friction stir welding. So in this, let's say I have a two metal workpiece. So I need to join these two things. This is 1 and this is 2. So I will have a die. Let's say this is my die, which I will put it on this interface and I will try to rotate it very fast. So what will happen, because of friction, heat will be generated on these two, 1 and 2. Lot of heat will be generated, so this will increase the temperature. However, here the temperature would not be greater than, so this temperature is less than melting point of the material, so which is the solid state bonding. And this die will be rotated and diffusion will occur across the interface, as the atoms here have now enough energy because the temperature is like, let's say, 0.7 or 0.8 of melting. So these atoms have enough energy just to like bond with each other, like move across the interface. Hence bonding will occur, which will be a solid state bonding, remember. And now this die will be rotated throughout, and it will have a translation motion throughout the length of this. So this both sheets 1 and 2 will be completely bonded. So this is first type of friction stir welding. Another type will be, let's say you have a cylinder and you have another cylinder. Now you have to bond this. So this cylinder 2 will be stationary and you will rotate this cylinder, like, and you will create you will like both will be in contact with each other, and one workpiece you will rotate extremely, so that due to friction heat will be generated in this region and this will get bonded. So this is another type of friction stir welding, where one workpiece only you are rotating. Here you are rotating the die, here you are rotating a single workpiece, but in both the cases the temperature is less than the melting point of the workpiece. Hence, this friction stir welding is not a fusion welding process. It is a solid state welding process. Hence, the correct option is option D. Whereas in all the three processes, some melting takes place near the joint. I hope this is clear. Is it clear? Yeah. Okay, so we will close today's session. In next session, we will have again some part of manufacturing processes, mechanical metallurgy, and everything. So next in next meeting, I will mostly take on 2010 question paper if I am not wrong. So I will have like 4 questions of that question paper. 2012 question paper, almost all questions are complete from my side. So we will meet next Wednesday 6 to 7 for few more questions from some different question paper. If you have any doubts, you can ask. Otherwise, we can close this session now. Okay, if you don't have any doubts, let's close this session. Okay, bye. See you.